moving on, our last speaker for the day is Mayank Gupta, who will be speaking on Websocket Scale at Fractional Footprint. Mayank Gupta is the principal engineer at Dhruva. Please welcome Mayank to the stage.
Hi, good evening everyone. So I am Mayank. So I work as a principal engineer in the foundation technologies team at Dhruva. And today I'll be talking about WebSockets and how to scale them to a multi-millions of connections with in the most optimized manner with respect to memory and other utilizers. So moving ahead, so let's talk about the problem. So basically okay, so how many of you have a requirement or have developed applications in which you want to proactively send commands or communicate with the clients from the server? So usually we have our servers, our clients requesting some data from the servers and server responding to that data, right? But how many of you have requirements or have developed applications which require server proactively communicating with its client? Awesome. Okay. So yeah, today we'll be talking about the similar use case, right? So we'll be talking about scenarios in which we want our servers to send data to the client. Now, in this, the problem becomes bigger when we have multi-millions of clients who are connecting to the server, and we want this connection from, we want this communication to be real-time and persistent. So like multi-millions of clients being connected to our server services simultaneously. Okay, moving ahead to understand better, right? So we at Dhruva, we are into the data protection domain, and we have our agents or the clients as we call it running into the customer environments. And we want our server to be able to proactively communicate with its clients, request data in real time, to send sync and async messages. And then we have our customers who have millions of these clients installed, and then we have tens and thousands of customers, right? So the goal of this, the problem which we solve at Dhruva becomes, we want a persistent long learning connection between the clients and the server. We want the communication channel to be bidirectional. So by bidirectional, we mean that the client should be able to send data to the server, and at the same time, server should be able to send data to the client. And we want this communication to be both synchronous and asynchronous. And then obviously the scale requirement, right? We want multi-millions of active connections at any given point of time. Cool. So moving ahead. So now let's talk about the various or the commonly used approaches that the industry uses to solve this problem. So the first one is frequent poll. So in the frequent poll is a very basic or naive approach in which the client keeps polling the server and checking, is there something for me, is there something for me, is there something for me? And if there is something, the server responds back, or the server sends an empty response if there is nothing. Right? So frequent poll works, but it has its limitation when it comes to scale, right? Then talking about the next thing, the HTTP long poll. And so in HTTP long poll, the client again requests the data from the server, but if there is nothing, the server, instead of returning back, holds on that connection till a threshold or a timeout has been reached, or there is something that needs to be sent to the client. So once the server sends the data to the client serves the request and then responds back. And then there is WebSocket. So now, first let's discuss what are the limitations that we might face with long poll, right? So long poll, firstly, is not duplex, meaning only one party can communicate at any given point of time. So when the client requests the data from the server, if the server has something for the client, the server gives back to the client, and then client returns the response in a separate request. But simultaneously, both party cannot communicate. That is a duplex communication, right? Then per connection authorization. So as the client needs to poll the server, even though it's a long poll, for each poll from the client, you need to authenticate and authorize on the server side. And along with authentication authorization, there are latency problems and the higher server footprint, because you need to send a lot of data, and along with the actual payload or the actual data which is required for that business logic, right? And then the delayed detection of disconnect. So this problem is basically, so if a client pulls the server holds on to the connection, and suppose the client dies. So the disconnect of the client will be detected a bit later when there is something available on the server side and server tries to write on that connection, or the timeout has been reached. So these were the 4 major problems we faced with a long pull. So now let's talk about WebSockets. So how many of you know what WebSocket is, or like have used WebSockets in their server sides? That's a big number. Nice. Okay, so I might not have to spend much time on this slide then. So, but for all those who don't know, WebSocket is a communication protocol. It is a communication protocol on top of HTTP, and it provides a full duplex communication between the client and the server, and the communication is provided on the same TCP connection. So how it works is basically the client makes a HTTP request on the server with the appropriate upgrade headers saying that it wants to upgrade to a WebSocket communication. The server, on receiving the request, sees if it supports WebSocket upgrades, and if it does, it upgrades the connection to WebSocket. Now, what we mean by upgrade is that the server basically hijacks the underlying TCP connection, and then a persistent link is established between both the parties, and both the parties have the readers and writers on the underlying TCP connection. Cool. So moving ahead. So now we saw what a WebSocket is, we saw long pulse, we saw the challenges we faced with WebSockets. Now let's see what are the libraries that are available in Go, the commonly used libraries for WebSockets. The first library is the WebSocket implementation that is provided by the net HTTP package, the standard net library of Go. So this library is, although it is RFC compliant, but it has various limitations when it comes to our use case, and also it has some basic things which are not implemented, like the pings. So the servers can't send pings to the client, it can only respond to the pongs. And the official documentation of net WebSockets itself suggests to use alternative and more maintained WebSocket libraries like the Gorilla WebSocket. Now that brings us to the second package, Gorilla WebSocket, which is the highly and most commonly used WebSocket library in Golang. So this library is like, most of you might have heard about Gorilla WebSockets package and might have used that. And GOPHERCON WS is a third commonly used WebSocket library, which is performant but not that widely known as compared to Gorilla WebSocket. Now, so this is how a sample code, WebSocket code would look like if we write. So whenever a new WebSocket connection comes, we have a HTTP response writer and a request. So as soon as we get the request, we initialize the upgrader object of the WebSockets library we have, and we ask it to upgrade the connection. Once the connection upgrade is successful, we have a connection object which has both the reader and writer. And then, like you can see in this for loop, we can read the messages as and when required from the underlying connection, and we can similarly write to that connection object as well, until and unless the connection is like closed or the link is broken. So moving ahead. So okay, so now we saw what a WebSocket is, we saw how a basic code of WebSocket looks like, right? So now whenever there is a communication from a client to server, right? So by the HTTP listen and serve method, how it works is, for each connection request, a new Goroutine is spawned. That Goroutine actually calls the serve function of the HTTP listen of the package, the HTTP package which we use, and then inside that serve function we serve that communication. So consider your million clients having a persistent connection with the server. You will have million open Goroutines, right? So with million open connections, with million Goroutines running, we have various challenges related to memory utilization. The next problem is the problem of synchronization. So as we just saw, WebSocket is a sync communication protocol in which a persistent link is established between the client and the server, and both parties can write on and read the data from the underlying connection. So we can't have synchronization. So at any given any given point of time, the client can write the messages and can respond to the messages received from the server and the vice versa. And then horizontal scaling. So horizontal scaling is obviously a challenge because in WebSocket, a persistent connection is established between the client and the server. So, even if you have multiple instances of your server machine running, the client at any given point of time will connect to a particular instance of your server, and then you can only communicate to the client through that instance because the connection is established on that instance. So let's try to solve each problem one by one. So let's understand the memory issue with the normal or the basic implementation of WebSocket, right? So we have a Goroutine. That Goroutine calls the serve function, right? Inside the serve implementation of our HTTP package, we allocate few buffers. So one is the writer buffer allocated by the standard HTTP package, then the reader buffer which is allocated by the HTTP package as well. And then the WebSocket lib which we use, that hijacks the underlying connection and allocates another HTTP writer buffer. So in all, 3 buffers are allocated, and the size of each buffer is 4 KB. And then as a Goroutine is spawned per connection, so we have additional around approximately 8 KB of memory that is utilized by that spawned Goroutine. So if you sum this up, approximately 20 KB of your memory is utilized per connection from client to the server. So if you have million clients just connecting to the server and doing literally nothing, just having a connection, persistent connection, WebSocket connection established with the server, you will be utilizing approximately 20 GB of RAM. That doesn't work, right? I mean, your company will say, yeah, this doesn't work for our COGS, right? Either you give your salary or you reduce the COGS. Okay, so let's try to solve that. So how many of you know Epoll, what Epoll is? Okay, quite a few. Right. So Epoll is a kernel system call which provides a scalable I/O event notification mechanism. So what Epoll does is it monitors multiple file descriptors, and whenever there is any I/O available on the file descriptor which it's monitoring, it raises a notification or it invokes a callback. So now to understand how we can use Epoll here is each open TCP connection from the client to the server is basically a open socket connection, which is in turn a open file descriptor. So for each connection, we have an open file descriptor. So we can use that file descriptor and pass it to Epoll saying, please monitor this file descriptor for me, and whenever there is any I/O on that file descriptor, notify me. So now you don't really need a million Goroutines waiting for messages from the client or just sitting idle if there is nothing from the server to send to the client. So you can have a single Goroutine which for Epoll, and you can pass all those file descriptors to Epoll, and whenever there is any notification, you can serve those requests either by spawning a Goroutine, either having a pool of Goroutine, or in the same request as you like it, right? So now we saw a code how WebSocket works, how our connection is upgraded to a WebSocket connection, and then we have a net.connection object, right? So after you upgrade your connection to net.connection object, what you can do is we here have utilized the netpoll library of Golang for Epoll. So we fetch the file descriptor in read once mode. So read once meaning Epoll one shot. So for that connection, and then we pass that file descriptor to the poller, and we say start watching this file descriptor, and whenever there is any event on that file descriptor, invoke this callback function which is passed as the second argument. So now why we used Epoll one shot and why not some other mode? Because suppose your client wants to send a huge chunk of data on the underlying connection. So what happens is in Epoll, those data comes in a set of packets. So it is quite possible that for a single package or a single message, you are receiving multiple Epoll notifications. So to avoid that, we use Epoll in the Epoll one shot method. Okay. Now we don't need one Goroutine for each connection. So our memory utilization is approximately equal to the memory which is utilized by the buffers which are WebSocket library allocated, right? So here we have reduced our memory utilization by approximately 30%. But that's not enough, right? Still our salary is at stake. So let's move ahead. So now we need to optimize those buffer allocation. So like I keep saying, it's a persistent connection, it's a async communication protocol. So we don't really need buffers to be allocated as the connection is established. We can have our buffers allocated as and when required. We can have a pool of buffer, or we can have a single buffer. So we wanted to have a library which does not allocate the buffers as soon as the connection is established. And also, as we saw, two buffers are allocated by the HTTP call, the reader and the writer. And as a part of a hijack, a writer buffer is again copied into a new buffer by the WebSocket library. So the GOPHERCON WS WebSocket library provides a solution to all these three things. So it does not allocate any intermediate IO buffers. It has low-level APIs for handling packages and buffers. So it provides more granular APIs, and it does not copy the buffers like Gorilla WebSocket did or the Net HTTP WebSocket library did. So now we are not allocating buffers as well. And by this, the memory utilization is reduced by 60%. So if Epoll and this GOPHERCON library is used, so we ran our experiments for 1 million connections, and we found out that the total memory utilization was drastically reduced to by 97% to 600 MB. So 1 million connections which were earlier consuming 20 GB are now consuming just 600 MB. Now my boss is happy and my appraisals are good. Okay, so first problem solved. So far, so good. Let's talk about the next problem, the synchronization problem. Okay, so here there are various ways in which communication, async communication can be synchronized. We can use queues, we can use some other third-party libraries, but we are using Go and we have channels, and those are magic, right? So why not just leverage channels instead of using any third-party thing to optimize the buffer allocation? So in this, what we did was, whenever any server service wants to communicate with the agent, and it wants to say that I want this communication to be a synchronous communication. So whenever a sync message is received, we generate a random UUID for that particular message. We create a channel with that UUID, and then we send that sync message to the agent. Once that message is written on the underlying WebSocket connection, the request through which we received from the server service to the WebSocket service, that request keeps waiting on that channel. Okay, now the request is stuck. The client receives the message, it takes its own time to process that message, and it writes the response. The client, while writing the response, writes the same UUID which we sent earlier. And when that message is read at the WebSocket server service level, it checks if a channel exists with that UUID, and if it does, it writes to that channel. The earlier request, which was waiting on that channel, now receives the response message, and the response is sent back to the server. So in this way, we synchronized a synchronous communication just by using channels and no third-party library. Cool. Let's move ahead. Synchronization solved. What about horizontal scaling? Still a big issue. Now, we at Dhruva, we have like almost all of our server services deployed into AWS, and then AWS has various services which are available out of the box, like the auto scaling groups, the load balancers. So we try to leverage those to horizontally scale our server services, just like we scale any other server service. So what we did was, we had an auto scaling group which used to scale up and scale down a WebSocket server service based on some memory, CPU metrics, and all those stuff. Now, we just used the lifecycle hooks of the Amazon auto scaling to say that whenever you scale up an instance, you first create a DNS in the Amazon Route 53 and assign that private DNS to the newly spawned instance. And then what a newly spawned instance will do is, it will register itself to a registry service saying that I am a new instance which will serve WebSockets communication from the clients, and this is my IP and this is my instance ID. Our server registry has this information now. Now, whenever a client wants to connect to the server, the request is routed through a network load balancer. The load balancer, based on the best possible algorithm, will forward that request to one of the instances of the WebSocket server. Whenever the request is connected to the WebSocket server, the WebSocket server, before upgrading that connection to WebSocket, it first stores the mapping in the server registry saying, this device is connected to this instance. Now we know which device is connected to which instance, and for each instance, what is its DNS. So far, so good. The connection is upgraded, a connection is established. Now, whenever any service who wants to communicate with the client, it will just fetch the instance IP to which the client is connected and will send the request on that particular instance of WebSocket. And then we have our own intermediate caching and everything to optimize this further. But this is how we can now horizontally and almost infinitely scale our WebSocket server services. Third problem solved. Thank you.